Okay, so I'm going to outline how the NHSX contact tracing application works from the ground up. So there is an issue around contact tracing, and especially where we resolve someone who could be a carrier to a certain location. So in some places in the world, it is possible to location track someone who is infected and who could be a carrier of COVID-19. So to increase trust from citizens, we need to make sure that their privacy is preserved in some way. So the NHSX app really focuses on certain key features in that very little personal information is passed and only with the active consent of the user. It is then not possible to trace the user or the device from the Bluetooth beacons that are sent, apart from being in close proximity to a phone. It shouldn't be possible to spoof the data of another user to the system. And then it shouldn't be possible to see if the person is a carrier of COVID-19 from the information sent. And there's also a robust mechanism against users to be able to replay any information. So here is a basic outline. First, Bob downloads an app and then actively registers onto the system. The health authority, his public key is sent, and Bob will be generated a symmetric key, such as for AES, and also an installation ID. Over here, those are stored on the main cloud provider's system. The only information which is taken is the postcode information from here. It will be these two elements which will then be able to resolve back to Bob again. So when Bob comes into contact with Carol, then Carol's ID will be encrypted in some way, and then there'll be a log on the phone which stores the signal strength and the risk score. When the risk score is high enough, then that information will be sent through Firefox Firebase log infrastructure to this cloud provider here, and then NHS will have complete access to that data. So the way it works is that initially we generate a secret here, and that will be the private key of the health provider. We then generate a public key, which is S times G. G is the base point. We're using P256. We have a base point on an elliptic curve, and we add that base point S times, or we define that as S times G, or we multiply the base point by S time. So this is an important element here. Then each day, Bob will create a new random value, his private key, and then creates a daily public key. He will take the base point and multiply it by G to get his public key from there. Then we create a value Z, which is the elliptic curve Diffie-Hellman exchange between the server and Bob. But it doesn't have to happen here. All that needs to happen is that the Z value is calculated. Basically, the way it works is that we have S and B for Bob, and then we pass those values across, and over here we end up with SBG. Bob will also end up with SBG for Z, and this will be the shared key that is used to be able to protect Bob's identity. As I said, there's no reason for the exchange to happen just now. The server will regenerate the value of Z later. So then we derive a key derivation function using the value of Z that we've just created, and also the public key of Bob. With that key, we then take a message with his ID in there, and then we encrypt that with the key that we've just derived with the initialization vector, the salt, and we create our cipher. The cipher is then placed into a broadcast message along with the public key of Bob, the country code, and some other things. When Bob comes into contact with Carol, the BV value, the encrypted value of his identity, is contained in there, and that's appended on with the public key, his public key that he's using for his daily key, and along with the transmission power of the Bluetooth transmitter, transmission time, and then we have an authorization code which is signed by his symmetric key. So only he will be able to sign that broadcast. When Carol then sends that forward, the server will take the BV value and extract Bob's daily public key. It will take its own secret value, S here, and derive Z. Z is equal to S times R times G. We take Bob's public key and we basically multiply it by S to be able to get Z. From Z, it's then easy to take Bob's public key and generate our encryption key, and then after that it's easy to be able to decrypt this this cipher here, and then once we have that, we'll be able to get Bob's ID, the message in there with his country code and the start and end dates and so on. So obviously one risk is that if this key here is discovered, then all of the IDs will be released. So this key needs to be stored securely. The public key can obviously be known by everyone, but the secret key needs to be unknown and private at all times. Okay, so that's been an outline of the NHSX contact tracing.